Okay, thank you, Ayan. I almost feel a little bit embarrassed now that you sort of have introduced me as sort of a leading sort of physicist. I don't think that's what I am, but I try to do stuff that I have fun introducing and sort of working out. So that's the spirit of what is going on in this talk today. So basically, I would like to talk about a set of recent papers that I have been involved with together with my collaborators, Oliver de Wolf and Saga Seppi. And basically, as you can see already from the beginning slide here, what I'm going to propose is that that there are ways to do strong coupling calculations without the use of holography. And that's basically what I'm going to report on today. To get started, I have in my title slide a picture of Boulder. So this is the University of Colorado Boulder. You can sort of see the stadium here, which of course is the most important building on campus. The physics building would be over here. These are these towers. And this is also where the famous JILA laboratory is located. And for those of you who have never been there, Boulder is located right where the Great Plains, which are on the left of this picture, go over to the Rocky Mountains, which are to the right on this picture. So it's a sort of fairly sort of sweet spot to be at. But for reasons that would take too long to go into this talk today, I am currently not in this building here, but I'm talking to you from a different city. I'm talking to you from Salzburg, Austria, where I have taken refuge from whatever is going on in my sort of adopted home city of Boulder, Colorado. So without further ado, I will go on and jump into the subject that I want to tell you about today. And I want to start by motivating what I do by just reminding you of a few statements having to do with a particular gauge theory having to do with n equals 4 super UMLs. So this is a gauge theory that I think most of you are now very well familiar with. It's a four-dimensional quantum field theory with gauge fields, fermions, and scalars. And it is a supersymmetric field theory. It has one coupling constant, the 't Hooft coupling, lambda, which you can relate to the gauge coupling G as lambda is G squared n. And the number n is basically the corresponding number of the sort of SUN gauge group that this model has. It has the specific and unique property, or almost unique property, that it is exactly conformal for all values of n of the gauge group and all values of the coupling lambda. It also is interesting because it can be solved at weak coupling in perturbation theory and also in strong coupling using the ADS-CFT correspondence. Because I will sort of talk about many of these observables in the following, I would like to start by telling you a little bit about the thermodynamics of n equals 4 super UMLs. So you can put the theory at final temperature T using the usual formalism, for instance, imaginary time formalism. If you do so, that will break supersymmetry because basically the final temperature breaks the supersymmetric invariance. And you can go on to calculate thermodynamic observables such as the entropy density S. At weak coupling, the result that you get is the free entropy density S free, and it is given as some prefactor that scales at large n as 8n squared, where n again is the rank of the gauge group, times 2 pi squared over 45, T cubed, that is the temperature to the third power. It has to be that way because of dimensional reason. And then I wrote it in such a way that you have a 1 for the contribution of the, if you want to, H gate field that contributes, and the fermions, which contribute exactly 7/8 of one bosonic degree of freedom for every fermionic degree of freedom in 4 dimensions. So if you take this together, you find that the free entropy density of n equals 4 super UMLs is given by this result here, 2 pi squared T cubed n squared over 3. And you can compare that to the corresponding result at strong coupling in large n, which was calculated using ADS-CFT. And you find that the strong entropy density is given by a number 2 pi squared t cubed n squared over 4. And if you compare these two numbers, you find that the strong coupling result for the entropy density is not equal to the RHIC coupling result for the entropy density. In fact, it is exactly 3/4 of the free entropy density. Now, a little bit of history. Originally, it was thought that this 3/4 was a mistake. So when first the strong coupling result was calculated, the people in the paper sort of noted that it is almost the same as the original one, and they sort of brushed aside this difference. Maybe some of them even thought that there was a mistake in the calculation, but it turns out that it's not the case. It actually is a different value. It is exactly 3/4 of the free result. One can also look at corrections to both the weak and the strong coupling results for the entropy density. This is summarized in this very beautiful plot here that I've taken from this paper here, where S, the entropy density, is scaled by the free value, now denoted as S naught in this plot here, and it's plotted as a function of the tooth coupling. So for weak coupling, this is normalized to 1, so it starts at 1, and then it decreases because the weak coupling correction is basically negative, so it sort of has to decrease in this direction. And at very large coupling, lambda to the infinity, which is not visible on this plot here, it has to go to the 3/4, 0.75. One can calculate correction also to the strong coupling limit. These basically sort of have been evaluated here, and they sort of come in with a strong coupling correction that's lambda to the -3/2, and that is positive. So that's basically says that from strong coupling part, you get a positive contribution. And then you can sort of attempt to sort of connect these two regimes, the strong and the weak coupling regime, by doing various, I would say, tricks of various sophistications. One of them sort of is a Padé approximation, where you just take the strong and the weak result, and you basically put one in the denominator and the other one in the numerator, and you sort of force the coefficients such that they get the right limits. You can also do more sophisticated things like a resummation of the weak coupling result. This is this NLA here, for instance. And for these, you find sort of different curves, which are indicated by these different lines here, that kind of seem to suggest that there's a monotonic decrease from the weak to the strong coupling side, so from 1 to 3/4 in n equals 4 superemils. However, nobody has calculated the actual result of this curve, S over S3, as a function of lambda, even though in principle this is a well-defined theoretical problem.
Well, I'll point out that we did HDLPT also for this and recently, and it agrees very well with the NLA band.
Okay, thank you, Mike. Yes, I didn't mean to be exclusive, and this is certainly not.
No. I just want to point out that although there's some you might have some worry about the resummations that are done. Now, 2 different resummation schemes give you the green band. That's all.
Okay, thank you very much. Oh, and by the way, whenever I put up the slides, you can look at the actual papers by clicking on the hyperlinks in the PDF. So just to reiterate, n equals 4 superemils is exactly conformal for all couplings. Some people call this a pure CFT because it's exactly conformal not at just one value of the coupling, but all couplings. It certainly would be nice to study other examples of pure CFTs if they exist. It would definitely be nice to understand why such funny fractions as 3/4 appear in n equals 4 superemils. Maybe this is also just a coincidence, or maybe there's some deeper sort of reason why you get exactly 3/4. It would definitely be nice to solve QFTs for all values of the couplings. For instance, connecting these strong and weak coupling result that I showed you on the previous slide from the first principle calculation, even if it was only at large n. And these sort of are certainly some points that provide a motivation for the sort of topics that I want to talk about today. So let me sort of try to answer some of these questions. Namely, I first want to talk about pure CFDs different from n equals 4 superemils, and long story short, there are other CFTs that are pure CFTs. The easiest examples of those that I could find result if you are allowed to change the number of space-time dimensions. So for various reasons, it's much more convenient to go to 2+1 dimensions or 3-dimensional field theories and study those. These are honest QFTs. There's nothing wrong with them in principle. You can think of them as being, if you want to, the study of quantum field theory in flatland where space only has 2 dimensions, or if you want so, somewhat strange model for certain condensed matter systems that are effectively 2-dimensional, such as graphene. In particular, what I want to talk about is an n-component vector model with sextic interactions. The Euclidean Lagrangian for this theory is written in this equation here. So it has a usual kinetic term. I am in Euclidean space, so there's no difference between, so basically all of the indices are just downstairs. It's a vector model, so it has n components for the scalar phi, and it has this sextic interaction, which is phi squared to the 3rd power, which gives you a phi 6 term effectively. This theory also has one coupling term, lambda, which sort of arises in this particular form here. And what I'll do is I'll claim that this theory defined by this Lagrangian is a pure CFD in the large n limit. I will say essentially nothing about finite n corrections. I will just talk about the large n limit of this theory. So it turns out that at large n, this particular vector model can be solved exactly for all couplings, which is another one on the point on the list that I had in the motivation section of my talk. The solution that can give you this result actually sort of is not new. It's really sort of decades old, and you can sort of read papers by Zingerster and others, or the book in Zingerster, to sort of educate you about the large N models. My contribution is just to, if you want to do some archaeology, dig up these results and sort of try to put them into a modern context, in particular, now that we know about holography. In particular, what you can do is you can get exact solutions for the strong coupling lambda to infinity limit directly from the field theory. There's no holography involved, no duality involved, no other sort of modern sort of trick involved. The actual sort of calculation, if you have never done this, takes a little bit of understanding. Nevertheless, I wanted to give a one-slide summary for experts. So if you have never done any of these calculations, this slide will not make a lot of sense to you, but don't worry, I can talk about the physics of the results without having you to understand the method of generating them. The way this works is that you insert unity as a path integral over some auxiliary field sigma times a delta function into the path integral of whatever you want to compute. Since our Lagrangian here had this sextic interaction, you can use the delta function to replace the phi to the 6th term by sigma cubed. So then the only phi dependence that you get is basically the kinetic term that's quadratic in phi. Next, you rewrite the delta function as an integral over a second auxiliary field times e to the I integral over these sort of fields. And again, you get a quadratic term in phi, so you can essentially integrate out the scalar field phi exactly. And the trick really to sort of make this a useful approximation is large n, because it turns out that the large n, only the zero modes of these auxiliary fields sigma and zeta actually contribute. This clearly sort of is the main key to the solution, because once only the zero modes contribute, all of the nasty 3-point couplings sort of drop out, and you have a well-defined simple integral over the zero modes that you have to solve. So as I said, the integration over phi is just Gaussian. It becomes trivial. What you get is a scalar field with a mass that depends on this auxiliary field, in particular the zeta. And in the large volume limit, you can also do those remaining integrals over the auxiliary fields from the saddle point. And if it's large volume limit, then these integrals are exact from the saddle, because all other corrections sort of die off as 1 over the logarithm of the volume. The saddle point condition from this integral then gives you a so-called gap equation for the effective mass. So if you want the value of the auxiliary field at which this is evaluated, and that's basically the end of the story. So jumping back to what this does for you, you find that there are large end results for this sextic vector model, and you find that there is a gap equation for the effective mass. This is an in-medium mass where I've written this parameter zeta as another parameter psi squared times t squared, where t is the temperature. Then the temperature drops out, and you end up with an equation that this parameter psi has to fulfill. And this equation here encodes the complete coupling dependence of this effective mass. Note that in the large n limit, this is an exact result. This is not a weak coupling concept of an effective mass. This is the whole thing, essentially. A trivial check is that you find that if the coupling constant goes to 0, you find that the effective mass parameter also goes to 0. So that's something that you would have expected. The interesting thing really happens at infinite coupling. This equation here has a solution at lambda to infinity, and it's given by the following result. The mass parameter for infinite coupling goes to twice times the logarithm of the golden ratio. You also find that once you sort of go through this exercise, you can calculate the entropy density. The result to find at any value of lambda is given by this equation 6 here. It depends on n t squared, because we are now in 2 + 1 dimensions. There has to be t squared, not t cubed, as in 4 dimensions. And a dimensionless number, that's just a purely implicit function on the coupling through this mass parameter psi. There are some polar logarithms here, but don't get distracted by those. And you can sort of look at what this entropy density does as a function of the coupling. Particular for vanishing coupling, I said that the mass parameter goes to 0. So that means that you have to evaluate this function for mass parameter goes to 0. And you can find that at the end of the day, these sort of functions come together in such a way that this result here gives you the free entropy density being 3 n t squared over 2 pi times zeta of 3, where zeta is now just the regular Riemann zeta function. However, it's also possible to evaluate this function for all values of the coupling by numerically solving the gap equation. I've plotted the result S over S3 here, and beware that that shows a slightly non-standard x-axis. Instead of plotting the result as a function of the coupling itself, I've chosen to plot it as 1 over 1 plus the square root of the coupling. The reason being that this way I can compactify the coupling interval from 0 to infinity in this compact fashion. So the whole range coupling from 0 to infinity is shown here, and weak coupling here is now on the right, and infinitely strong coupling is to the left. And what you're supposed to be seeing is that this is the exact result in the large n limit of this theory. It's a monotonically decreasing function and decreases from something like 1 to something like 0.8. At large n, then let's try to evaluate the result for the entropy density more closely in the infinite coupling limit. So I told you that for 0 coupling, we have the free entropy density given by this result here that I discussed. We can also use the identities of this polar logarithm function having to do with the fact that at infinite coupling, the mass parameter goes to twice the logarithm of the golden ratio, and then polar logarithm identities let you figure out that the result for the strong coupling case is this result here. So it's 12 n t squared over 10 pi zeta of 3. Again, you find that's not the same as the free coupling result for the entropy density, but instead it's exactly 4/5 of the free entropy density. This result was, to my best of my knowledge, found first by Subir Sachdev in 1993, and then recovered by a number of authors, for instance, by a paper of Drummond et al. In 1997, and also sort of newer ones since then. In particular, I've also found this more recently. To reiterate, what we have here is we have a pure CFD at large n, It has the property that its trace anomaly is vanishing exactly at large n, so you get a vanishing beta function for all values of lambda. The entropy density is monotonically decreasing as a function of lambda. There is a strong weak relation for the entropy density that is, I would say, very much reminiscent of what we found in n equals 4 superuniverse. So in this sextic scalar model in 3 dimensions, we find a strong weak relation for the entropy density of 4/5, whereas for n equals 4 superuniverse in 4 dimensions, we found 3/4. As I sort of tried to say, there is no holography or duality used for this infinite coupling result. It's just from purely standard methods. Let me pause at this moment and try to sort of give you the main flavor of what I think this means. So it turns out that for scalars, the large N thermodynamics can be solved at all couplings directly from the field theory. At this point, we should ask ourselves, well, that's nice, but if we can do this, what else can we do? Can we do transport? Can we calculate E/S? Can we calculate out-of-time order correlators? Can we do fermions and gauge fields? Can we maybe sort of turn holography on its head and actually use the large N quantum field theory result that we have control over to derive holography? And I don't mean derive in the sense that, oh yeah, there should be some duality that's corresponding to this, but actually derive the equations of motions, the properties of a quantum black hole, and if you want so, quantum cosmology from the field theory. Well, as you can probably tell, I have essentially not many answers to these questions that I am asking here, but I will tell you what answers I found or what sort of path towards answers I found in the following rest of the presentation. Nevertheless, I wanted to use this as a moment to see whether there are some questions from you guys.
I would have one, if I may.
Sure, go ahead.
So this is leading order large N, right? I'm just where you only have the mass shift essentially. Is it conceivable to go to next to leading order actually?
It is certainly conceivable, but there are two problems with this. The first problem is technical. At 1/n, there are a lot of sort of terms that appear, and it's not clear how to sort of do a sensible truncation of this that would allow you to get analytic results for the 1/n correction. The second one is actually conceptual. Unlike the large leading order large N result, it is not clear that there is a sort of well-defined way that gives you essentially the 1/n result cleanly, if you want to. I mean, certainly you can expand in 1/n, but the physics of that sort of carries some sort of nasty sort of couplings that are difficult to express. So I think it's worthwhile to sort of investigate whether it's possible to have, if you want, a next to leading order treatment that includes all the 1/n effects, but potentially more than that, and follows and gives you a closed systems of equation that you can solve.
Yeah, okay. Yeah.
I tried to sort of go a little bit in that route in another paper of mine, but it's not easy.
Yeah.
But certainly, I mean, yeah, so certainly it's an interesting direction to go in.
Well, what we've seen so far is in 3 dimensions, right? And usually when we go from 4 to 3 dimensions, you know, the infrared behavior of theories change.
Yes, it gets harder.
So what prevents us from doing such? Yeah, what prevents us from doing such a treatment in a 4-dimensional theory?
Nothing. And I will actually show you the results for the corresponding 4-dimensional theory towards the end of my talk.
Okay, good, because I didn't understand why it would be specific. Of course, if you want to do it, you have to do it right in the 4D theory. Right. Thank you.
So I mean, okay, so I can already sort of give you the punchline. So basically, the advantage of going to 3 dimensions is that in 3 dimensions, you don't have logarithmic divergences. So there are no anomalous dimensions. This is a huge simplification, and in particular, it means that your beta function is just trivial. Whereas in 4 dimension, your beta function for the scalar theory will be positive, so you will have a lambda pole. The lambda pole will prevent you from going to infinite coupling because you just have a sort of energy scale beyond which you can't really probe. In 3-dimensional theories, that problem is absent. You can go to infinite coupling without any problem.
Thank you.
Okay, so then maybe let me go on a little bit further to see whether we can get to some of these results that I just alluded to. Let me first try to sort of see what we can say about correlators. So if you wanted to go, okay, historically, thermodynamics is, if you want to, the lowest hanging fruit. If you can get thermodynamics at all couplings, that's nice. But really what you want to do is you want to go beyond. You want to talk about real-time dynamics. You want to talk about transport. So that's what motivated me to look at real-time correlators at large N in this particular theory. I get started by considering a Euclidean correlator of the energy momentum tensor, which I describe in this way here. So this is the TXY correlator. The energy momentum tensor correlator, the energy momentum tensor component, TXY is just given by this particular sort of result here. And if you go to large N, there is a major simplification in calculating these correlators. I would invite you to look at the sort of very readable sort of paper by Juan Maldacena in this Tarsi lecture from 2019, where he goes on and sort of tells you why it is that at large N, essentially only bubble graphs contribute to these correlators of this form that have they have phi squared correlators at each point. But it turns out that if you are interested in this particular correlator here, the TXY correlator, then it actually is even easier than that. And the reason is that you have these XY derivatives, which essentially sort of lead to different momentum space entries when you do Fourier transformations. And essentially because you can't have an integral with just, well, you can't have a non-vanishing integral with just one value of momentum sitting in there, because by essentially parity, this integral will vanish. It turns out that for these particular correlators, all except the trivial bubble cancel for this particular correlator. So that's very nice. So you find that in momentum space, the exact large N correlator for the energy momentum tensor is just given by this object here. It's a single it's a single sum integral over momenta weighted with kx squared ky squared and two propagators of the scalar field, where the only information about the coupling resides in this mass parameter that's in the propagator here. So basically the statement is that at large N, the exact correlator TXY involves a single loop integral. The structure of this loop integral only depends on the coupling through this non-perturbative mass parameter. So for this particular reason, we can actually obtain exact real-time info at large N via analytic continuation. The easiest thing is to first consider zero external momentum K. Then you can analytically continue the Matsubara frequencies to real frequencies, and you get a retarded correlator, GR of omega, that's just given by the analytic continuation from your Matsubara frequencies to real frequencies using the usual rule. For this particular result that I showed you on the previous slide, you find the following result for the retarded correlator. It's an integral that sort of has this structure here. It involves the Bose-Einstein distribution function. It involves the energy that cares about this mass parameter here, but overall, this doesn't seem to be impossible. Long story short, it turns out that you can solve all except for one of these integrals analytically. And the remainder of this integral, I sort of recast into an infinite sum. So here's the result. You find that the retarded correlator TXY for this field theory in 2+1 dimension is given by the following results. There is some result which I care about, and there are some analytic terms that I've written out in the paper, but don't want to repeat here because I'm interested in the analytic structure of this correlator here. So you find this can be written as an infinite sum over n, where you have something in the denominator that depends on your frequency, and there's a logarithm in the numerator here that also depends on this frequency. And there's this parameter psi, which again is just the mass parameter that I talked about in the beginning of my talk. So if you stare at this result for this correlator, you find that there is an implicit dependence on the coupling only through this mass parameter here. There's no explicit dependence on lambda. I should also say, maybe I didn't mention this, normally when we sort of calculate correlators in, for instance, perturbation theory, there's a sort of dependence on the renormalization scale, because this quantum field theory in 2+1 dimensions at large n is essentially finite. It's a finite quantum field theory. There's no renormalization, so there's no dependence on some renormalization scale. This is the exact result. At first glance, it looks like this correlator has a pole here at omega is I times 4 pi n or something like this. However, you see that that's not really true because the values where the denominator would vanish, that's exactly when the logarithm here sort of goes to 1. So you have the logarithm of 1 is a 0. So you have 0 divided by 0. So that's not really a pole. It's just not a singular structure at all. To me, that sort of is very much reminiscent of the phenomenon of pole skipping that we saw in Sasha's talk. However, Sasha tells me that's not clear yet. Really, what I should do is calculate the finite momentum corrections to this and see whether there's actually pole skipping happening. So I think this is an interesting avenue to go and check. Also, if you look at this, you would say, but there is a logarithmic singularity that comes from the numerator here, where essentially the value of the omega is such that you sort of pick up the mass. But it turns out that's also not true, because wherever this numerator in the logarithm, the argument of the logarithm is 0, that's exactly where the prefactor also vanishes. So you don't get a non-analytic, you don't get a singularity there either. Okay, basically what you've there, yeah, right. So basically what you find is that there are no singularities in GR. It's analytic, except that it also has the branch cut that's sort of emanating from this singularity that would be there if you didn't have the prefactor. So there's a logarithmic branch cut, or there's 2 logarithmic branch cuts, depending on the definition. But there is no actual singularities in GR. It's basically regular everywhere. Now you might say, okay, this is fine, but you've talked about a very, very particular quantum field theory. This is this one example of these pure CFDs that are conformal everywhere. It's a very special result. So maybe it doesn't really tell us much about quantum field theories, generally speaking. So basically, the idea would be, well, can we say something that's more generally true than what I just told you about this very specific theory? We can check, or we can try to check, the universality of this result, SOS3. And one way to do that would be to essentially sort of take our result for the sextic coupling that we had and just change the coupling, okay? Don't look at sextic coupling, look at arbitrary potential u of phi squared and see which result remains and what changes. The only requirement that I'll have is that this potential u is not allowed to lead to symmetry breaking, okay? So it has to have only one minimum at x is 0, otherwise you get spontaneous symmetry breaking and the results really change. So if you allow this one condition on a general potential wu, you get maybe some surprising results. You find that the strong coupling mass, this twice logarithm of the golden ratio, is actually independent from the value of u. You find that the strong weak thermodynamic ratio is actually independent from u. You always get 4/5. And you also find that the strong coupling result for GR is independent of u. So no matter what u you choose, you always get these 3 results. Essentially what you find is that there is universality at infinite coupling for a very, very broad class of bosonic field theories at large n. I want to sort of go on and ask whether we can further generalize this result. because n equals 4 supermills has scalars, fermions, and gauge fields. I talked a lot about scalars. Let me sort of see how we do if we try to add in the fermions in addition to the scalars. So essentially, if we do that, we might as well try to do supersymmetric theories. Okay, if you have fermions and gauge and scalars, we could build supersymmetric models. N equals 4 is supersymmetric. So let's sort of use that as a first step. There is a model in 3 dimensions that's large N and supersymmetric. It is the Wess-Zumino model. And that's basically the model that we studied in May of last year. So essentially, field content for the Wess-Zumino model is that you have an n-component scalar, phi a, and you have Majorana fermions psi a, where a again sort of runs now from 1 to n. The Lagrangian at large N is sort of given by this result here. You have a kinetic term for the scalars, a kinetic term for the Majorana fermions. There is a self-interaction term for the scalars, which has to come out as phi cubed in this result. And there is a sort of interaction term between the scalars and the fermions. There's one coupling constant, lambda, and this result, or this Lagrangian, is supersymmetric at 0 temperature. It is another example for a pure CFT, which is a CFT, a conformal-free theory at all values of lambda. The theory can be solved using exactly the same trick that I showed you before. Doesn't change anything, and you get a result for all values of lambda now for this Wess-Zumino model. I'll just flash the result for the masses. There are now 2 masses here because they are bosons and fermions. The bosons here at weak coupling again is here to the right. The bosons, which are here in black, essentially have exactly the same qualitative behavior as for the purely bosonic theory. They vanish at 0 coupling, and they go to this twice logarithm of the golden ratio at infinite coupling. The fermions do something more interesting. The fermions also start out at 0 at weak coupling. They reach a maximum mass, immediate mass, at some intermediate coupling, and then they go back to 0. You can also calculate the strong or the ratio of entropy density to free entropy density. Again, weak coupling is normalized to 1, and you find it's a monotonically decreasing function, and it ends up at some value over here that I'll comment about in a moment. So in particular, let me call your attention to the strong coupling results for the Wess-Zumino model. The fermion masses are vanishing, which just means that the fermions at infinite coupling are free. The boson masses are the same as the ON vector model, twice the logarithm of the golden ratio. And the thermodynamic ratio, as strong or as free, is also a fraction. You can understand why it's a fraction by looking at in terms of this way. So the free entropy density for a field theory in 3 dimensions is the following. It contributes, it has a contribution from the bosons, the scalars, which are sort of normalized to 1. And the fermions, unlike in 4 dimensions, only contribute 3/4 of a degree of freedom for the theory in 3 dimensions. So this is this fermionic 3/4 here. And at strong coupling, the bosonic contribution gets reduced to 4/5. That's the same 4/5 we saw before. And the 3/4 of the fermions remains the same because the fermions are free at infinite coupling. So basically, you find that the strong to free entropy ratio for the Wess-Zumino model happens to be a ratio. The ratio is 31/35, whatever that means. So basically, you find that the strong coupling results. Sorry, I sort of got ahead of myself. So what you find is that there is a kind of universality also for the Wess-Zumino model. You find that the strong coupling results stay unchanged if you break the SUSY. So if you start playing with the potential and go away from this sextic potential that I had for the supersymmetric theory. The strong coupling results also remained unchanged if you change the interaction potential. So basically change the coupling between fermions and bosons. And the strong weak thermodynamic ratio really only cares about the number of bosons and the number of fermions you have in your field theory. If you generalize it to B bosons and F fermions interacting with pretty much any kind of interaction, you find that the strong weak ratio happens to be 4/5, but 3 times the fermions over 4 times the bosons over the free result. And that's bounded between 4/5 at the sort of limit where you have basically only bosons to 1 if you basically have only fermions. So there's an inequality here that tells you that for an extremely large class of field theories in 3 dimensions that consists only of bosons and fermions, the entropy densities must be bounded between 1 and 4/5, 1 and 0.8 at infinite coupling. Turns out that this inequality holds true in even larger class of fermionic theories, and I point you to a recent paper by Marcus Pinto in this regard. Okay, so I already said that 3-dimensional field theories are special because the log divergences are generally absent, and that's really a huge simplification in terms of technicalities. There is clearly a lot of overlap with a huge literature on these web of dualities in 3 dimensions that have to do with CFT results. It's not completely clear to me how much of these results that I told you could already have been gleaned from these existing web of dualities. However, the thing that I wanted to stress is in terms of the tricks that I used, none of these tricks depend on dimensions, and all of them just carry through to 4 dimensions or 5 dimensions or 6 dimensions or whatever dimension you want to calculate in. So now I want to use the last few minutes of my talk to actually consider regular 5-4 theory, scalar 5-4 theory in 4 dimensions, to just tell you what changes if you go to field theories that we usually care about. The action that I want to consider is given in this equation here. I want to first start in curved spacetime. So I have a Ricci curvature R that's in here. I have a metric tensor G. My scalar field is again an n-component scalar field that has the usual kinetic term. It has a 5-4 interaction because it gives me a marginal coupling, at least naively. And I want to include this term with the Ricci scalar here because I wanted to point out that there is a particular value for this constant that's multiplying this term here, which is 1/6. If this alpha, the constant here, is exactly 1/6, we refer to this model as a conformally coupled scalar in 3+1 dimensions. It also happens that you can define transport coefficients for the theory by, for instance, calculating functional derivative with respect to the metric. And there's one particular transport coefficient, this curvature matter coupling coefficient kappa, that then can be found as, can be found from calculating the energy momentum tensor correlator, Euclidean energy momentum tensor correlator, and the square of the field phi. That is basically the action of this conformally coupled term here that we find here. And this is a result that was derived by Pavel Kovtun and collaborators 2 years ago. So essentially, if we are able to calculate these correlators, we can do this derivative here and get this transport coefficient in 4-dimensional quantum field theory. The disadvantage of doing 4-dimensional quantum field theory with a positive beta function is that the theory has a lambda pole. In some sense, this theory is trivial. However, we can think of the theory still in some effective sense, that we don't go exactly to infinite coupling, but we go to strong coupling, and at some point, the presence of the lambda pole will lead to an ambiguity that we can test for by varying our scale or something like this. So that's basically the way that I want to employ these results for scalar field theory in 4 dimensions. It turns out that the result you get for the transport coefficient kappa is divergent. It has a UV divergent unless this value of alpha that I had in my previous slide is exactly 1/6. So for a conformally coupled scalar, I get a finite result of kappa without any additional randomization, whereas for different values of alpha, I would claim that kappa is not defined for this theory. If you do the calculation, it's a calculation of a correlator that I told you, at least in principle, how to do in 3 dimensions. You just do the same of steps in 4 dimensions. You find an analytic result for this transport coefficient kappa. It's given in this equation here. It's minus 13 times n t squared bosonic mass squared over 2,520 times pi squared. And the MB, that's the E-medium scalar mass. The MB is the solution of this gap equation here, which depends on the renormalized coupling, lambda. It also depends on your randomization scale, mu. So that's basically what was absent in 3-dimensional field theories. You never had to deal with these kinds of things. In 4-dimensional theories, you just get them back. So you get an analytic result for this transport coefficient. You can plot it. That's the way it looks. So this is kappa in units of nt squared as a function of the coupling. Weak coupling is over here, that the transport coefficient vanishes. And you basically find that you sort of have this trend for this function here, where as you get closer and closer to strong coupling, you get more and more sensitive to how you deal with the lambda pole and the physics of the lambda pole. So that's meant to be represented by the size of this band here that's probing for the cutoff sensitivity. Clearly, when you couldn't do transport, you clearly can do thermodynamics, and in particular, you can calculate things like the speed of sound. So I thought that it would include this slide here, which is the speed of sound squared minus 1/3 for this model, 4 dimensions, as a function of the coupling. So 0 coupling is here, and then as you increase the coupling, the speed of sound exceeds 1/3. And you find that for this particular theory, at large n, there's an exact result that says CS is strictly larger or equal to 1/√3. And you can link it to the fact that you have a uniquely positive beta function for this theory. Okay, so this is an example for a field theory that violates this, I don't want to call it a bound, this sort of statement that field theory should have speed of sound less than 1/√3 in 4 dimensions. Here you have a field theory which clearly violates this, and you can show why that is. I'm almost out of time, but I still wanted to say a little bit about gauge theories, okay? So I told you how to do fermions and scalars at large n. Gauge fields. So gauge fields are a little bit of a problem. The best I could come up with was to do QED with a large number of electrons in 3 dimensions. And that's basically what I report on. So essentially, this is a theory called QED3 for QED in 3 dimensions. It has a very nice property. It's, again, exactly solvable for all values of the coupling in the large number of electron limit. At 0 temperature, this particular theory with a critical number of flavors of about 4 has been suggested as a model for chiral symmetry breaking a long time ago. In 4 dimensions, large enough QED thermodynamics has been studied by a number of papers by Guy Moore, Andreas Ipp, and Anton Repan. However, as was the case with the field theory that I discussed before, in 4 dimensions, QED, large enough QED has a lambda pole, so you can't really go to infinite coupling. You get sensitive to the physics of the lambda pole. This complication is absent in 3 dimensions. So QED3 is well defined for all couplings. It's in principle a solvable theory, so one should look at the results. Nevertheless, QED3 contains some surprises. If you look at it naively, you find that there's an apparent uncancelled UV divergence at 4-loop order. If you deal with that in a way that is described in the paper, which I don't have time to go into, you find the following result for the large enough pressure for the theory. So I don't plot the entropy density. In this case, I plot the pressure. But it's the same idea. So you start at weak coupling, and there your pressure is 3 times the number of electrons plus 1 for the gauge fields. It starts out monotonically decreasing until a sort of critical coupling here, and then something complicated, I want to say, happens. Basically, in our paper, we claim that we think that eventually theory goes to this point here at infinite coupling. But in particular, because of these questions surrounding the apparent uncancelled UV divergence, there's still, I would say, some lingering questions about whether the theory actually does this. note that QED3 is not a conformal field theory. Okay, so this has non-vanishing energy momentum tensor, has a non-trivial beta function. It is basically very much like a fully grown quantum field theory with all the usual problems. But I would claim that in 2+1 dimensions, the theory is well defined, and in principle, there's an answer to, in particular, things like the pressure that should be amenable to non-perturbative calculation. With this, I wanted to summarize. I've talked about theories with scalars and fermions that can be solved analytically for all couplings in the large N limit, irrespective of whether they have SUSY or whether they are conformal field theories or not. I also mentioned very briefly at the end QED3 as a gauge theory with many number of flavors that can be solved semi-analytically. And I wanted to remind you that in the case of three-dimensional conformal field theories, one recovers QED results such as the strong weak duality of the entropy density of 4/5 that are very much reminiscent of this mysterious 3/4 factor that has been known from holography for N equals 4 superunions for a number of years now. Beyond thermodynamics, the same set of tools offer you access to at least some of the correlators for arbitrary value of the coupling. And basically, maybe my main message is that holography actually is not the only tool to study large coupling dynamics. And with this, I want to thank you for your attention. And if there are more questions, I'm happy to address them as much as I can.
Thanks, Paul, for this very nice talk. And well, I think there will be very few who would disagree that you are one of the most versatile physicists, actually, I think. So let's take questions then. Sasso has at least 2 questions for you.
Okay, hey, Paul, can you hear me?
Yes, I can hear you.
Thanks for this. This was a very nice overview of your recent papers. Very much enjoyed this. So I have a question, maybe with a few sub-questions. I was curious, if you take one of your exactly computed S's, right? S as a function of lambda, and you expand around lambda equal to 0 and lambda equal to infinity, what kind of series do you get? I mean, are they convergent or divergent? Are they just power series? Or do you also get logs? I was asking about these logs, Mike, at some point, and he was expecting some logs in n equals to 4. So I'm curious.
Right. Yeah. So basically, have a look at this result in equation 8 here. So that's the result for the entropy density. It is implicitly depending on the coupling through this function, so this mass parameter psi. And psi itself is a solution to, where was it? This equation here. Okay. So I'm pretty sure there are logs of the coupling. I haven't tried to study what the corresponding character of this series is, but I think this is a very good suggestion. I think there's nothing stopping you from just expanding the equation, the solution to the equation here in a power series of lambda, and then sort of plugging in here to sort of get the corresponding result of the observable, such as the entropy density. I'm not completely sure that it's easy to sort of do that fully analytically, simply because, I mean, it's not as well. I don't think there's an analytic solution to this equation, for instance. So and there are polylogs over here. So I'm sure you can do it sort of just by brute force and enumerating the first, I don't know, 10,000 terms or something like this, and looking at the series this way. So that's a good suggestion. One can definitely sort of try to do this.
Okay, yeah, I was curious. Maybe it would help. I mean, at least to me, to what kind of expectations one should have of these series, because normally you cannot just get an exact result. Okay, so I mean, the other sort of, I mean, I guess I saw your last example, but the question was if these functions were always monotonic, but I guess except in this QED at the end, which is weird, it looks like they're monotonic, right?
Yes, I mean, okay, so I don't have any statement about monotonicity. Okay, so basically, I know that people in theoretical physics have been obsessed with trying to prove or disprove monotonicity of something like the number of degrees of freedom for decades. There are a number of theorems that go by the names of C theorem, F theorem, and so on and so forth. So basically, I think that for the entropy density, no such theorem is known to exist for more than 2 dimensions. In 1 + 1 dimensions, there are theorems such as the C theorem that guarantee you this for CFTs. But for higher dimensions, that's generally not the case. People have then changed the question and sort of, instead of looking at observables such as the entropy density, they have defined other observables such as the free energy of a sphere.
That's right. Yeah, that was my question, because that's the F theorem in 2 + 1 dimensions. If you would put your theory in the sphere, then maybe you can say something about entropy.
Yes. So basically, the F theorem sort of, okay. So it's actually pretty interesting. Essentially, what you can do is you can calculate I calculated here, if you want, so the free energy for the theory on an thermal cylinder. Okay, so the space-time here, the 2 + 1 dimensional space-time, because you have the Euclidean circle, and then you have the sort of other space-time dimensions that go out, is a Euclidean cylinder. But there's nothing stopping me from changing geometry and sort of doing a sphere. So you do it on the S3, and it happens if you calculate the free energy on the S3 for a conformal field theory, you basically sort of get the entanglement entropy of a circle. You can calculate that as a function with a circle with respect to the rest of the space, as a function of the coupling. And that basically maps to this free energy. So you can calculate the corresponding entanglement entropy as a function of the coupling, just as the one that I've done here. And you find that in the large n limit, that quantity is constant in the coupling. It does not change. The only changes that come in from 1/n corrections. This is where the F theorem sort of goes in. But at leading order in large n, unlike the thermodynamic entropy that does this, the entanglement entropy is just constant.
Okay, all right. Okay, thanks. Yeah, that's yeah. All right, thanks for the answers.
Actually, I have a related short question. I understand the monotonicity is not something to be obsessed about, maybe, but it seems like if you have fermions, pure fermion theory, it goes to 1, so it should not be monotonic, right? In a pure fermion theory. So does adding fermions typically make the monotonicity worse, or is it,
I'm not sure that I completely understood your question. So basically, there's this one example, the Wess-Zumino model, that has both fermions.
Exactly. So,
and you can, I don't have it side by side, but that's the corresponding plot for the Wess-Zumino model. It's monotonic. It maybe is not as steeply decreasing, in particular close to infinite coupling.
No. This was not the slide I was referring to, actually. I was referring to this particular, I don't remember the slide number now. You had the number of bosons versus number of fermions, and yes, exactly. So here it seems like if you're a pure fermion theory, then you go to 1, you saturate the upper bound. So the monotonicity would be kind of less, would not be there, right? In the limit on pure fermionic theory.
Right. If you have a free fermionic theory with no coupling to anything else, then indeed the entropy density just doesn't change. Okay, it's just a free entropy. It's just a free Fermi theory because there's no coupling anymore. If you have just fermions. Yes. So that's why it goes to 1. Yeah.
Okay. All right. So Sayantan has a question. Please ask.
Hi, Paul. Thanks for your very nice talk. So I was wondering if one does perturbation series, suppose, in these kind of theories for small values of lambda, these are also asymptotic, right? Or
well, good question. I think this is essentially what Sasha asked previously, and I don't know the answer to that. I think one can try to get the answer to that, at least semi-analytically, by brute force calculating the first couple of thousand terms. But really sort of, I mean, I think you can sort of code this up in a few minutes, right? I mean, you take the sort of result for the immediate mass. So where was it? this one here. You basically sort of do a formal expansion in the coupling parameter, and then you sort of have to plug it into the observable here and calculate term by term what the coefficients of these series is. Is it asymptotic? I don't know. I can't tell you. I haven't tried. I think it's not hard to do, but I haven't done that. So I can't tell you right now.
So there are these recent discussions that all these sickness of the perturbation theory is related to some non-perturbative physics. So is it possible to see in these kind of theories where everything is analytically under control? So are there any?
I mean, there's a hint already, right? I mean, in principle, when you do perturbation theory, you do it in powers of lambda, but this non-perturbative equation that you have to solve involves 1 over square root of lambda. So I think that's already sort of some hint that something non-analytic is going on, but it's clearly not enough to sort of prove that in any sense of it.
Yeah, so I would like to extend Sayantan's question. Like in n is equal to 4 superangles, you either have the perturbation series in lambda or the perturbation series in 1 over square root lambda. You don't have a trans series, right? So this, I think the class of theories, maybe this very special class of theories where you could get these kind of nice universal results, maybe.
That's possible. I mean, clearly n equals 4 superangles is a much richer theory than the theories that I've studied here. Whether it's obvious that their sort of character in these solutions sort of is obviously asymptotic or non-asymptotic is something that I would like to check before I sort of say something concrete. But I think we can all agree that n equals 4 superangles is clearly a much richer theory in that regard.
No, I'm saying that n is equal to 4 probably falls in this class because it is only a lambda expansion or a 1 over square root lambda expansion. So you don't have to add them together. Maybe this is also what is happening here. And maybe this class of theories has this kind of universality of the ratio of S strong by S weak. Maybe
okay,
I'm just,
okay.
Yeah.
Okay.
Okay, Mike has a question now.
Not really a question, more like a comment. So I just wanted to say that it's very interesting. But it seems to me like one of the next steps that should be followed is to try to relax the large n limit assumptions, right? And see how all this picture changes. So go to whatever the simplest case in which you can do this. I think that would also be very interesting.
I mean, yes, I totally agree. I mean, clearly the naive large n limit, that's really where the easy stuff is. I'm old enough now that I can do only easy stuff because for everything complicated, I have to hire someone. So essentially, you can see that it is very interesting to include the 1 over n corrections from a number of points. I mean, one of them, for instance, is that I told you that I would like to calculate things like transport coefficients e to s or stuff like that. So it turns out that for the theories that I've shown to you, in the large n limit, you don't really have sensitivity to those transport coefficients because it turns out that there is some funny thing going on where the 1 over n term that is naively sort of suppressed for, well, it is suppressed for thermodynamic properties, for instance. For things like e to s, it is the 1 over n that's appearing in the denominator. So it actually is an n term. It's actually sort of more important than the usual sort of contribution. You kind of can see this already through the fact that in weak coupling, your e to s, for instance, in 4-dimensional theories, goes like 1 over the coupling squared. So that clearly says that there's these properties are sort of, they don't easily sort of fall into this class of a regular 1 over n expansion. I think that it would be really interesting to see if one can come up with observables that are sensitive not to the viscosity, but to 1 over the viscosity. I don't know whether these observables exist, but I think those would have a much, much better characteristic in terms of expansions in perturbation theory, strong coupling, 1 over n, all of these things. So yes, I mean, I fully agree with you. I think it would be very nice to do 1 over n. I have some theories in mind where I think this is easier than in others, but it's still not easy. So I guess I have to hire someone.
It reminds me of I was in an INT meeting once, and people were talking about large N limit, and as a young student, I just blasted out from the class, well, why don't you just compute the corrections? And everybody just laughed at me.
Okay, so the final question would be from Søren.
Yeah, well, I guess it kind of got answered on the way. I mean, I was I wanted to come back to this issue of transport coefficients or eta, right? So they are so this is something you simply cannot do in the large N limit, right? Because essentially it's I mean essentially they're like, I mean, you only have the mass correction, right? That's all that happens to your propagators, right? So at the end of the day, your propagator is almost like a non-inter. I mean, it doesn't have a structure, right? It's just a delta peak, so to say, the spectral function, right?
Yes. So from that point of view, all the things that I've shown you are completely uninteresting. I agree with that. The only exception to the rule is QED in 3 dimensions.
Mm-hmm.
And my expectation is that the easiest transport coefficient of all that you could try to calculate in these class of theories is the large NF electric conductivity in QED3. Now, it turns out that I have tried to go in this route and calculate this transport coefficient. I have a result for infinite coupling. The problem is that nobody believes that this result can be right. I have been sitting on it for a year now. I'm not sure if it will come out, but I think still that is the easiest transport coefficient where one can at least think about doing that.
Yeah, I mean, it would be super interesting if somehow the 1 over n correction, so to say, could be achieved, right? I mean, I can only weigh in with what Mike said there. Oh, but this is great stuff.
Maybe just a small comment about. So you were saying that you're looking for an observable that would be 1 over the viscosity. I mean, I don't know what that is, but if you're looking for something that's 1 over the conductivity, that I do know. So that, you can have in magnetohydrodynamics, you have resistivities, which are approximately 1 over conductivity. So such a thing does exist. I mean, I don't know
what's the correlator that gives you that directly?
It comes from the 2-form current. It comes from from F dual.
Right, but that gives you that gives you a conductivity from the Kubo formula, right? And from that you can calculate the resistivity, no?
No, we computed we in this paper with Nabil Iqbal and Diego Hoffman, where we introduced these higher form symmetries for MHD. We have a Kubo formula that's a direct Kubo formula for resistivity, not going through conductivity.
Very nice. Can you send me a reference to that?
Yeah, sure. Yeah, we have Kubo formulae directly in terms of a correlator that gives you the resistivity, and we actually commented there why we believe that resistivity being equal to 1 over conductivity will be only true at weak coupling, because otherwise there are extra graphs contributing to this. I'll send you the paper. Yeah. So I thought that this would be very interesting in this QED with dynamical electromagnetic fields, not when they're static.
Yeah.
Okay. Thanks.
Thanks.
Okay, thanks again, Paul, for this great talk.